So the problem is that if I generate the density matrix by integrating out wave function, so I need to solve for the wave function. I am again going back to 3n dimensional problem. Instead, what happens if I try to get the density matrix directly without even resorting to a wave function? For a special case of single determinant wave function, of course, I can write the first and second order reduced density matrix in terms of orbital. This is how the form looks like. This is for the one body reduced density matrix, this is from the two body reduced density matrix. Also, for the single determinant wave function, what you can do is that it can be shown that the two body reduced density matrix can be written as a product of the one body reduced density matrix. So, this is a special case for a single determinant wave function. Remember, this cannot be done when the wave function is not a single determinant. For any correlated method, this relation cannot be done. So, that means I cannot get why I say that this cannot be done, because when I am going from one body reduced density matrix from two body reduced density matrix, I am integrating out the coordinate from of R2. So, that means I am doing a reduction of the information. So, there is no unique way of going back from rho 1, gamma 1 to gamma 2 for a general wave function. For a single determinant wave function, you can do that. Since gamma 1 can be obtained straightforwardly integrating from gamma 2, if I can somehow get gamma 2, I can actually get the energy, because we have shown that the energy can be exactly written in terms of one and two body reduced density matrix. So, if I somehow can guess the gamma 2, I can actually get to the one body reduced density matrix, and gamma 2 is actually not very bad. It is 4 coordinates, and each of them can be x, y and z, but it is still better than 3n, right. So, like it is 4 times 3 at max 12, but it is still better than the 3n number of coordinate. So, if I can get the gamma 2 somehow directly, then I do not need to go to the wave function picture, because for energy I do not need the higher order wave function. So, it seems very attractive that if I somehow can get a theory where I can solve the gamma 2 directly without going into the wave function picture, maybe some kind of a variation doing it, I can directly get the energy and my problem becomes much more simplified. And these theories are called density matrix theory. Remember, this is different from density functional theory, where the energy is written as a function. In the density functional theory, energy is written as a functional of density. That means only the diagonal element of the one body reduced density matrix. Whereas in density matrix theory, my energy is written as a functional of one body and two body reduced density matrix. So, if I can guess the two body reduced density matrix, my problem is much more simpler. What is the problem? Problem is that the gamma 2 elements cannot be varied freely, because remember how these gamma 2 elements were generated. They were generated by integrating out an antisymmetric wave function, because I am dealing with fermion, and that is when you do the integration and reduce down to gamma 2, it is very difficult to ensure that this gamma 2 was actually correspond to an antisymmetric wave function, because my information has been reduced due to the integration. So, that is what is called an n representability problem. That is why although the density matrix theories are very attractive in principle, they are not really practical. At least there is no practical way of solving them. One can do instead is to go to so called density cumulant functional theory. So, where gamma 2 can be written as a product of gamma 1 and a remainder term. So, for a one body reduced density, we have seen that for the Hartree-Fock theory, you can write the gamma 2 as a product of gamma 1. And here what is done is that you write it for a general wave function also, you write the gamma 2 as a product of gamma 1 plus some correction factor lambda 2. Now, this cumulant lambda 2 term account for the pair correlation. So, how this gamma 1 actually interact among each other, and they also must implicitly ensure the representability problem. So, this gamma 1 in this case, remember, it is not a simple one particle reduced density matrix, it is a sum of the idempotent component as well as a correlation term. So, this include not only the simple one body reduced density matrix, it also has a correlation part included into it, and this first term, the idempotent part, is actually correspond to the orbital product for a single determinant wave function. So, if I go to the single determinant picture like a Hartree-Fock picture, this will become like an orbital product and this tau term will become 0. So, this actually goes back to the simple Hartree-Fock picture. This is the beauty of this thing, And of course, you can actually solve for this gamma, but to do that you need to solve nonlinear equations like couple cluster. So, basically density cumulant functional theory is practically tractable theory, people work on that, but the problem is that to get it correct you still need to solve nonlinear equation like couple clusters. So, the advantage is not as much what you envisaged in a density functional theory, where you can write the energy in terms of the density only, the diagonal element of the reduced density matrices. So, now let us go to the density functional theory. So, we have discussed density matrix theory, density cumulant functional theory. Now, we will go to the actual density functional theory. And so density functional theory is not a very new method. It actually almost started as same time as Schrodinger equation, slightly later than that. The first few attempts to do density functional theory was actually to do the exact density functional theory for a model system. So, these are not applicable on an exact molecular system, but these are some model system where you can solve the density functional theory exactly. So, density functional theory as it is for certain system, this is an exact method. So, this is like it will give you the same energy as solving for the Schrodinger equation only through the density, not anything else. However, for all practical applications, what modern density functional theory does is that it solves the density functional theory equations approximately for a real system. So, what was done previously is to solve exactly for an approximate system, whereas now what is done is that you solve it approximately for a real system. So, what was done in that orbital free DFT is that you know that we have 4 terms. T is the kinetic energy, this I have now written as electron nuclear attraction, I have now written as E, I could have written as V also, not a problem. This VE is electron repulsion and VNN is the nuclear repulsion, which is a scalar term. Now, this VE may be divided into Coulomb and exchange term. We know that the physical 2 electron interaction can be of 2 types. One is where any negatively charged particle will avoid each other, that is a Coulomb part, and then there is an exchange part where electrons of same spin will avoid each other because of the antisymmetry. Of course, there is a correlation contribution. So, when I am dividing the VE, this is the exact VE. So, it is not only the Hartree-Fock Coulomb on the exchange part, it also includes the Coulomb the correlation part. Now, the nuclear electron attraction and the Coulomb part of the correlation energy can be written only in terms of one body reduced density matrix. This we have discussed before, we have not of course went into any formal proof. So, this is what electron nuclear attraction can be written only in terms of density. The electron repulsion, the Coulomb term, the J, the Coulomb is in the Hartree-Fock we discussed, the Coulomb is always denoted with J and exchange is denoted with K. So, this can be also written in terms of density. Now, that means if for an uniform electron gas, what do I mean by uniform electron gas? That means the electron density is constant everywhere. So, that is a fictitious system which is called a Gelium, sometimes it is called Gelium also. So, here the electron density is actually uniform at every point of the space, which is different from the molecules. Remember CO picture, there was a cusp in the nuclear position and there is a variation in the density. So, for the exact system the density changes from point to point, but from an uniform electron gas the density is same, and for that one can derive the form of the kinetic energy functional, which only depends upon rho, diagonal element of the reduced density matrix, whereas for the one body reduced density matrix, whereas for the exact case the kinetic energy functional depends upon the density matrix, not only density. And similarly I can also derive a form of the exchange which was already given before, and if I write the energy in terms of this Thomas Fermi kinetic energy. So, of course, this kinetic energy is called Thomas Fermi kinetic energy, and nuclear electron attraction and this Coulomb term, this is called Thomas Fermi theory. What is the problem of this theory? First problem is that there is no exchange, and why exchange is important? Remember what happens in the Hartree-Fock is the exchange what it gives you the stability. So, that is one problem. So, the electron, so the stability what comes due to the antisymmetry and exchange, this will be missing in this theory. This is another more problem. So, the way we have written the Coulomb term, that means each electron will also feel an interaction with itself, and that is what is called a self interaction. Remember, in the Hartree-Fock, the self interaction was not a big problem, because the self interaction term, what happens due to the Coulomb, was exactly cancelled by the exchange term, the corresponding term in the exchange. So, Hartree-Fock theory itself was a self interaction free theory, but here, because there is no exchange, there will be self interaction in this case. So, what you need to do is to go to Thomas Fermi Dirac model, where the exchange contribution for the uniform electron gas is derived like this. This derivation was actually made by Bloch, but it is attributed to Dirac. So, now if I put this form of the exchange, I will get, in the previous Thomas Fermi model, I will get a new form of the functional, that is called the Thomas Fermi Dirac model. That is actually an exact form of the energy for an uniform electron gas. But the assumption of uniform electron gas may be fair for valence electron in certain metallic systems. So, physicists love this kind of theories, Thomas Fermi Dirac theory, because it is an exact theory without any approximation, only depend upon density. So, it does not matter how large system you are studying, it is not a problem. But this is very poor approximation for atoms and molecules, because we have seen that in the case of molecules there are cusps in the density. So, density actually is changing. So, you cannot just write the simple formula for electron nuclear attraction, kinetic energy, Coulomb and exchange term. Moreover, this Thomas and Fermi kinetic energy further leads to an incorrect asymptotic behavior. The electron density is supposed to decay exponentially, whereas what happens in the case of Thomas Fermi model, so this is how the electron density is supposed to decay. If I calculate the electron density for helium in some quantum mechanical model, I can calculate the wave function and then calculate the density. I will see that it will have an exponential decay. Whereas, if I do the Thomas Fermi model, I will see that it will decay r to the power 6. So, this actually gives you a wrong behavior. Second thing is that the atoms actually has a cell structure. So, we know that there is a periodic trends in the atom, that Thomas Fermi model totally fails to recover. And neither Thomas Fermi model or Thomas Fermi Dirac theory predicts bonding. So, it does not give you a bound energetic structure for any molecules. So, that means Thomas Fermi Dirac model, although it sounds very attractive because it can write the energy in terms of only density, it is not of any use for any practical calculation in chemistry, because it cannot even describe molecules. So, I cannot use that. Of course, one can do the Weizsäcker correction. So, you can expand the kinetic energy terms in terms of a Taylor series and include the higher terms, but that also does not give you very good results. So, that means although the exact density functional theory is very attractive in terms of its in philosophical appeal, it is not actually practical. So, what I need to now go back is to rewrite the theories in such a way, so that I will introduce the concept of orbitals, and then I will get to an approximate solution of the density functional theory in an exact way, and because this approximation comes, density functional theory will show how, but it will almost becomes like a semi empirical theory. But before going into that, let us go into the formal proof, not proof actually, just the theorem which says that a unique functional which maps the density for any system, even for molecule, should actually exist. And we may not be able to find out the form of the functional, but in principle it is possible to find such a kind of a functional. So, that is what we will go into the next lecture.